Yesterday we had the activity where we were able to explore the parametric curves by looking at the x separately and the y and then putting it together on an xy plane. And so I'm hoping that that idea is clear, and so we're going to pick it up from there and just start talking about parametric equations, and then we'll quickly move to the next section and do some calculus of parametric equations. So section 10.1 in your textbook talks about how a parametric equation is defined. It's defined by two equations, x and y, with an independent variable t. And then as t varies, t is going to be the input variable. As t varies, your x and y will change, and then you would follow along whatever is happening to the x and y. So formally, the definition of parametric equations is a pair of equations with one variable, independent variable, and then as you graph it with x and y, you'll see a curve, and the resulting curve is called the parametric curve. And so we saw some examples yesterday, and so let's just take a look at a family. So I'm not going to go ahead. I'm not going to construct a table or anything like that. But let's talk about some families of curves and then draw them out as examples. So families of curves. So as an example, I just got this from the textbook, and there are different families of curves that you can come up with. Let's pick one of these and try to draw them out. And what I'm going to do is I'm going to ask you if you guys have your calculators or if you guys have a computer out. You can find some sort of graphing program. Desmos.com, I think, might have some graphing programs. Except I don't know how they graph parametric equations and those things. But I'm going to take out my calculator, and I'll show you how to do this on a TI-83, 84, 89 might be the same thing. But this is not your usual function y is equal to f of x. So let's first pick one. Let's pick, which one should we do? Conchoid? Let's do this one. So in your graphing calculators, if you have them, you have to change the mode for your graphing calculator. So if you click on mode and go to where it says FUNC, that's the default mode, and that's the kinds of graphs where you can graph y is equal to f of x, y is equal to sine x, y is equal to x squared, stuff like that. There's two others that we're going to explore. The PAR stands for parametric, the POL stands for polar, and so we're going to take a look at those two. We'll take a look at polar in a couple days. And then the SEQ is sequences, so if you're interested in graphing sequences, you could do that, but we're not going to do that in this class. So I'm going to hit enter to select PAR, and then I'm just going to jump back to the home screen. Actually, I think I can just go ahead and click y equals. And when you hit y equals, you'll see immediately that your interface looks a little different. It's not y1 equals, y2 equals, etc. So it's y1 t equals, and then y2 or y1 t equals. So this is going to be your equation. Now, when we take a look at families of curves, they have the input variable t, but they also have another variable or another constant that you can assign numbers to. And in this case, the a is the one that's changing. So what we can do is we can assume a is equal to 0 or a is equal to 1 and then change that just to take a look at the different types of curves that we can run into. So let's start by saying A is equal to 0, and I'm going to explicitly put a 0 here for this A. So my equation is A plus cosine t. And then you can look for the t variable, but this button over here that says x, t, theta, n, this is your input variable for your functions. And so it knows that you're in parametric form, that when you hit that, you're not going to put an x, you're going to put a t. And then close parentheses. And then now I have 0 times tangent t plus sine t. Okay. So that's my function. Now, I could just hit graph and see what happens, but I want to be careful about making sure that this is going to have a good window. So I guess a good start would be to go to zoom and say zoom. One of those zooms is zoom fit. And then you can just adjust it from there. So I have no idea what this graph is going to look like, so maybe I'll do that first. I think zoom would do it. So if you hit zoom and look for zoom fit, it'll give you a suggestion, and then you can adjust it later on. Or you can hit zoom standard. It just that gives you a window from -10 to 10. I don't know if you guys are getting what I'm getting, but yeah, but mine is drawing it out. Do you guys have something like that? Let me show you why it's drawing it out. Let's go to y equals again. And if you look at that option on the left, if you move your cursor to the left, you can hit enter a bunch of times to see how it'll change the way it's going to draw things out. So the default is just a line. The next option is a thick line. The next option is a line with a circle. That means it's going to draw it out so you can actually visually see the graph being drawn out. And then it'll leave the trace. If you hit it again, then it's just a circle. And so that's just going to draw it out without the trace. And so that might not be good because you're just going to see the dot float around in your calculator. And then the last option is like a dashed dotted line, so it's more sparse. So if we just have the default and then we graph it, and then we'll see. Now I guess if we look at the equation, if A is equal to 0, then you have cosine t sine t, which we saw yesterday to just be the circle. This doesn't look like a circle. That's because your calculator stretches out its window. And so if you want to make it really look like a circle, you can go to window or zoom. There's another zoom for this. I don't know what. Zoom box? No. Zoom square. Ah, that's standard. That's a little small. You can play around with the zoom, or you can actually go to window and adjust it yourself. Now, if you look at the window window values, we have 0 and 6.28. So these are the values for t, the minimum and maximum values for t. And then the t-step tells you at what increments do you want this calculator to compute these values. And that's going to be important because if the values are too big, then you know what the calculator actually does? It doesn't draw a circle. It actually draws points, and then it connects those points with lines. If those points are close enough to each other, then when you see the drawing, it kind of looks smooth. But really, it's just a bunch of lines that it's trying to draw. And then the t-step tells you, how far to go before you put your next point. The x-min and x-max are going to be the values for your x values, and then the x scale tells you to put tick marks along the x-axis, and then that's the same for y. So let me see if I could just zoom in. So one more zoom in. Oh, that went too far. Whatever. All right. I got to zoom out now. So let's change the a. Let's try 1. So let's go back to that function. And then let's change the zeros into 1s. Or better yet, if you want to draw this as a separate graph, you can retype the whole thing again down for x2 and y2. So you can have 2 graphs going on at the same time. I don't want to retype everything, so let me just take a look at what happens when I put a 1 in there. And then graph. So something weird definitely happens. So I definitely want to explore this a little bit more. And if I want more control in zooming in and zooming out, instead of just zooming in and zooming out, I'm going to take a look at this and to say this is about 1. Maybe trace. So x is equal to 2, y is equal to 0. So my x value goes as far as 2. So I'm going to adjust my window to have my x-min maybe go a little bit farther down to -10. And then my x-max to go to +10. So, wait, I'm sorry, that's my y. I want my y to be that. I want my x-min to be maybe -1, and my x-max to go to about 3. And then now my y's, I want this to be a little bit bigger, like -10 to +10. Okay? And then I saw it being drawn out kind of quickly, but if I want to really take a close look at how it's being drawn out, I can go to this, this option again and click it so that it's the circle with the line. And then let's see the graph. So it starts up there and it goes, it looks like it goes up to infinity, although it doesn't seem like it's going up to infinity. And then it comes down, and then it starts again over here. So did you guys see that being drawn? Okay. And then let's do one more picture. Let's take a look at this when a is equal to 2. And then I'll keep the same windows, and I'll go ahead and graph it. So it kind of looks the same, except it kind of shifted a little bit, right? So that would describe one family, one set of curves. And we can see. So it would be good for you to be able to do this in your calculators in case, you know, say there was a quiz, and in the quiz it says, oh, graph a couple of members of this family. And then you just punch in your calculators and draw it on your paper. Right? All right, so let's see. If you have other graphing programs, though, that might be nice. So if you have other graphing programs that have a lot more control, you can take a look at this and assign what we would call a slider and see how it would look like as your parameter changes. And then you can look at it from, this has a lot more control, so you can change things a little quicker. To see what happens to your graph. And then the copying and pasting is a little bit easier too, so we can have multiple graphs on these things a little quicker as well. So just for the sake of having this in our notes, maybe I'll draw a few of them. And I'm kind of seeing this idea that it looks a little bit more interesting if I have values that are between 0 and 1, and then maybe a little bit past 1. Okay, maybe that's a little too messy. But we start off with a circle, and then I think the idea of a conch is these things where it has little loops in the sides. So we get a nice set of pictures to describe the family. That looks like a cool picture. Maybe we'll do it separately. Anyway, so this is the idea. It's just being able to graph it. And then somebody mentioned the vertical line test yesterday. And the idea behind this is that this is, when we say parametric functions, a set of parametric functions, the functions are x of t and y of t. So when you put those two together, x of t comma y of t, they draw out something in a parametric form. And the result that you get will be a curve that may or may not pass the vertical or even the horizontal line test. It depends if you know, the functions that you're dealing with are one-to-one and stuff like that. So you have to kind of look at it from a slightly different perspective than the functions that we've been looking at in the past. Okay? All right, now let's get into the next section where we're going to do a little bit of calculus on this. And the calculus that we're going to do is basically some derivatives, and then we'll do some integrals where we have to find arc lengths and areas and stuff like that. So let's take a look at derivatives. So in looking at derivatives, what we'll do is we'll construct tangent lines, and we'll find out information about the curve using tangent lines. And what we want to do is we want to look at the tangent line in terms of what's happening on the xy plane. And so the tangent line is, in terms of what's happening in the xy plane, is a dy dx kind of expression. So the change in y and the change in x. Well, that seems pretty simple because we could just look at the change in y function and the change in the x function. And so that's just dy dt over dx dt. And so change in y over the change in x. And so we want to see those changes. We can write the derivative of each of those functions and then put them as a ratio, rise over run. So this seems simple enough. Let's find an example. I meant to get into the homework. By the way, these due dates are tentative because the schedule's tentative, and so I'll make an announcement when the actual due date is due for these things. I don't want to purchase. So if you haven't clicked on the homework yet, this is how the homework would generally look like. And I'll do the first homework assignment here as an example. So for my function, I have t sine t, and then I have y is equal to t squared minus 9t, or plus 9t, sorry. And if I want to find dy dx, it's simply looking for the derivative of x with respect to t, and then the derivative of y with respect to t, and then putting it as a fraction. So dx dt. Looks like I need a product rule here. Derivative of the first times the second plus the first times the derivative of the second. And then dy dt 2t plus 9. And then if I just put that as a fraction, one over the other, then that's my dx, dy dx. Oops, but the dy is on top. So it's 2t plus 9 over sine t plus t cosine t. Okay, so let's check it. They want a fraction, so I should probably put a big fraction symbol over here. 2t plus 9 divided by sine t plus t cosine t. And then you can check your work, and hopefully we get it right. I got it right, so that's good. Okay. So that's a pretty straightforward thing to do. Let's take a look at one of the curves that we had as another example. What's that curve? This curve over here? Let's take a look at this curve with A is equal to 1. Which one's A is equal to 1?
No, without equal.
That one's over here. Which one's the red graph? Do you remember what A was with the red graph? 0.25. All right, let's do this graph with A is equal to 0.25. So let's do another example. We got x is equal to 0.25 plus cosine t, and then y is equal to 0.25 tangent t plus sine t. Okay? So let's find dy dt, or dy dx, sorry. So we need dy dt and dx dt. So dy dt equals negative sine t. Dx dt equals 0.25. What's the derivative of tangent? Secant squared t. Derivative of sine is positive. Cosine t. So this is our derivative for each of them. So dy dx is just a ratio of this. Oops. Okay. Any questions? All right. Let's take a closer look at that graph, and then let's talk a little bit more about it. This is our graph, right? So I don't think there's anything else interesting happening up on top. Let's see. Nope. Oh, maybe it doesn't go all the way up to infinity either. So anyways, let's take a look at this graph. I don't think there are any nice points here to pick. Let's pick this point, randomly pick this point. If you guys take out your calculators and help me out here. When t is equal to negative 10, where are you? Got a point? Yeah?
Wouldn't it be 4 secant squared t plus cosine t since we're dividing by 1/4?
I don't know. Do I have it backwards?
You know what I mean? You just put 0.25 up at the top, and if you're pulling the 1/4 from the bottom, it should be 4 times at the top, right?
Oh, this should be x, y. So I have this backwards? All right. Sorry about that. You think it'll be -4? Because the 0.25 is only attached to the tangent, it's not attached to the cosine. All right. Anyways, sorry. Let's get this fixed up. When t is equal to -10, what's my x and y value? It was fine before?
That part, the other part was switched.
Yeah.
That part was yeah.
Now is it good? Yeah.
Yeah.
All right, yes, I would like the answer. So -0.589 negative or +3. So that would be right here. So let's say you wanted to find the line tangent to this curve at that point. What do we need to find an equation of a line? A slope and a intercept. So we need x1 and y1. That's a point, right? So it looks like we have a point here. Do we have a slope? We have a slope. Well, kind of have a slope. A common mistake that people make in calculus, which I hope we don't make too much here, is that when you find an equation of a line, we have y minus whatever the y here is, 0.382, is equal to the slope times x minus whatever the x value is here. And some people would write this whole thing down over here as your slope, which is incorrect. Why is this answer incorrect? Because it's not the slope at that point, right? You actually need to evaluate at that point. So this is not correct. What we want to do for the slope here is we want to take dy dx and then evaluate this when t is equal to -10. So when we put t is equal to -10 in for the slope, then that's the slope that we're going to get for this. Is that clear? So I'd like for this to not be a common mistake, especially for Calc 3. And if it comes up in your exam, which it has in the past, make sure you evaluate and you get a value. So let's put 10 in there, negative 10. And then I'm just going to wait for an answer. I'm looking at the graph and expecting the answer to be positive. It's a positive slope, right? That tangent line that I drew there is positive. It's fairly close to 1. Yeah? 0.89, that's positive, fairly close to 1. But before I conclude that it's 0.89, actually I didn't conclude that. Can I have another person who's checking it confirm this? You gotta be careful with putting stuff with, especially when you're adding and subtracting with fractions involved. I mean, 0.89 sounds like a good answer, according to the picture at least. All right, we'll go with it. Of course, we could check. I'm going to go ahead and take that graphing program and check to make sure that we got it right. All right, let's see. There we go. That's at 2 o'clock. 2:10. It's 2:10. Okay. So that looks good. It looks tangent, right? It's a nicer picture than the one we have, so I'm going to go ahead and replace it. Any questions? Still pretty straightforward? Yes? That's because I confused you guys. It's the sign. This is a sign. Came from the x. So that's a dx dt. And then the one with the tangent that became a secant squared, that came from the y. Now your dy dx has this on top. The dy dt is on top in the numerator, and this is in the denominator. And so I would just leave it like this without trying to, simplify it. Does that clear things up a little bit? Are you talking about the order of the numerator, denominator? Yeah. Yeah, so the dy dt is the one that goes on top. And usually when you write things out, you write dy dt second, so it looks like it's in the bottom. But you just have to be careful where the x and the y are, and then the dx and dx dt, dy dt are.
I actually try to take the derivative of y first and x, so I don't get that mixed up.
So as long as you do it consistently now. Like, that's what I did the first page, the first time I did it, and then here I switched it back again, and then I got all confused. So make sure that when you're doing this, do it several times and then do it in a systematic way that you can remember. Or if you feel like you're going to be flexible about it, you can do it any way, any order you want, just as long as you keep track of where the dx dt and dy dt are. Okay? All right, so that's it with derivatives. Oh, there's also some stuff where you have to find out where you have horizontal and vertical tangent lines. So that's when horizontal is when the numerator is equal to 0, and vertical is when the denominator is equal to 0. So you guys can figure that out, I hope. The second derivative is unfortunately not as easy as the second derivative of y with respect to t and second derivative of x with respect to t. It's a little bit more complicated than that because we have to respect how those symbols work. And what I want to put here on the side is this is not equal to d squared y dt squared, which is the second derivative of y, d squared x dt squared, second derivative of x. Not that easy. So what you need to do is you need to look at the dy dx as a fraction and then take the derivative of that. You could think about using the quotient rule, yeah. So if you think about using the quotient rule, well, it's a little bit more complicated than the quotient rule because you're taking the derivative with respect to x, not with respect to t. So you want the dx squared, you want to take the second derivative with respect to x. And so what you need to do is you need to figure this out first, the dy dx, which is a function of t, and then you take the derivative of that with respect to t. So, yeah, I was going to do the example that we just did, but it looked like it might get too complicated. Oh, maybe it won't be too bad. Let's see. Let's find the second derivative of this. So we have the first derivative down here. Our second derivative says the numerator is going to be d dt of dx dy, or dy dx, sorry. So we want the derivative of this. Let's go a different color here. d dt of this thing, dy dx, is equal to, now I need the quotient rule. So it's low d high minus sine t, the derivative of the numerator, 0.25, derivative of secant, secant tangent, so it's 2 secant t times secant tangent plus, derivative of the cosine is negative sine. So this minus low d high, the derivative of the numerator. Boy, I need more room. Let's start that over again. So the denominator, derivative of the numerator, times the numerator, derivative of the denominator. The derivative of sine is positive cosine, but this is negative already, so it's negative cosine t all over sine squared t. So that's the derivative of dy dx. And so finally we get d squared y over dx squared to be this whole thing. Divided by what? The derivative of x with respect to t. Okay? All right. So let's say that's all the derivatives we can deal with for today. Tomorrow we'll talk about the integral side of the calculus of parametric equations by finding areas under the curves and finding some arc length stuff. All right?